In this video, we're going to do some practice problems using concentration, doing calculations with concentration. And what we're going to focus on is using dimensional analysis or unit analysis to solve these problems. So instead of plugging each number into a specific formula, we'll be using concentrations as conversion factors to get our answers. So I'll show you exactly what I mean. So we're going to start with problem number 1. A 750 milliliter bottle of wine is 12.5% ethanol, a type of alcohol, by volume. What volume of ethanol is contained in the bottle? So what I'm going to do for unit analysis is start by writing down one of the values that they gave me in the question. And they gave me a straight value, not a ratio or anything, of 750 milliliters. Okay. Now I have a conversion factor that comes from this concentration. And what they've told me is that 12.5% is my measurement for my volume of solute over my volume of solution times 100%. And what you can see from this concentration is that I can rearrange this formula into a conversion factor. So it's going to look like this. So if I had 12.5 milliliters of solute in 100 milliliters of solution, that would be the same as 12.5%. Of course, to get my concentration of 12.5%, I would take 12.5 divided by 100, and I'd have to use this times 100%. Okay, my milliliters cancel out. 100 being multiplied here, 100 being divided here. This is going to show you that this concentration of 12.5% is the same as a conversion factor of 12.5 milliliters of solute per 100 milliliters of solution. So if I use this conversion factor, I can multiply by 12.5 milliliters of solute per 100 milliliters of solution. Milliliters of solution cancels out. I'll be left with milliliters of solvent. That's perfect. They asked me what volume of ethanol is contained. So all I have to do now is plug it into my calculator. You can see that I have 750 times 12.5 divided by 100. And of solute. Let me just round to 3 decimal places, or sorry, 3 significant digits, since that's what I had in the question. So this is going to give me 93.8 milliliters of ethanol. Here's my answer. So when I set up this conversion factor, you'll see that I was multiplying these values. I did not set up equal fractions. I cannot cross-multiply and divide. I can only cross-multiply and divide when I've set up an equal sign between my fractions. And so the strategy here was to get whatever unit I started with in the denominator of my conversion factor so that they would cancel out. If it helps, you can think of my initial value, 750 milliliters, as a fraction in and of itself, where the denominator is just 1 with no units. Dividing by 1 wouldn't change the value of this at all. And so 750 milliliters is the same as 750 milliliters over 1. So we're going to try our next problem using concentration as a conversion factor. So sterling silver is an alloy that contains 6.5% copper by mass. What mass of sterling silver can be produced from 150 grams of copper? Now what I'd like you to do is pause the recording right now, try it on your own, and come back when you're ready. So my strategy is to write down the value that they gave me. That's not a ratio, just a straight value. I'm going to start with 150 grams of copper. Now I can multiply by my concentration, which is a conversion factor, but I have to make sure that I set up this conversion factor so that grams of copper is in the denominator. The whole point is for grams of copper to cancel, so that I will be left with grams of solution. And so my conversion factor here is that 6.5 grams of copper can make a 100-gram solution. Remember, in the last example, we showed how we can convert the percent concentration into this conversion factor by putting that percent over 100. Okay, so I can plug this into my calculator. 150 times 100 divided by 6.5, and your calculator should spit out the answer, 2307.69 grams of solution. So that's 2,307.69 grams. This is a big number, so let's just think about it for a second and see if that makes sense. So in sterling silver, there's a pretty small percentage that's copper. We have a decent amount of copper, and since it's supposed to be a small percent of sterling silver, yeah, we should be able to make a lot of sterling silver with this little bit of copper. I don't like this answer. It's such a big number. I think I'm going to convert to kilograms. The question didn't ask me to one way or another, but I think it's going to be easiest. So to convert to kilograms, we're going to move the decimal place 3 times, make this number smaller, we'll get 2.30769 kilograms of solution. And let me round to 3 decimal places. That's how many to 3 significant digits, since that's how many significant digits I had in the question. So this will be 2.31 kilograms. And my solution here is being called sterling silver. Here's my answer. Okay, so again, we used this concentration as a conversion factor. Let's try our next problem. Number 3, what volume of 30% weight by volume hydrogen peroxide can be made from 3.65 moles of pure hydrogen peroxide? So I know my weight by volume concentration is going to be in grams per milliliter. Remember that a gram and a milliliter are very similar units, even though one is mass and one is volume, because of the density of water. If we were talking about water, 1 gram would take up the space of 1 milliliter. The problem is this question didn't give me grams, they gave me moles. So I'm going to need a second conversion factor. I'm also going to need a value that can convert between grams and moles, and of course, that's going to be molar mass. So when it comes to hydrogen peroxide, H2O2, I have 2 atoms of hydrogen, each with a molar mass of 1.01, and I have 2 atoms of oxygen, which have a molar mass of 16.00, and so the molar mass of hydrogen peroxide is 34.02 grams per mole. Okay, let me go back to the question and see what value they gave me. That's not a ratio, just a number. And the one that they gave me was 3.65 moles of hydrogen peroxide. I need to multiply by this conversion factor that has moles of hydrogen peroxide in the denominator. This is 34.02 grams per 1 mole. So you'll see I just spread out those units, grams per moles, and I use them to make this conversion factor, grams per 1 mole. Moles and moles will cancel out. So for my units I have are grams, but I don't want to be left with grams. I want to be left with the volume of the solution. So now I need to multiply by my conversion factor, my concentration, that's going to have grams of hydrogen peroxide in the denominator, and volume of solution in the numerator. And so it's milliliters and grams that I want here. This 30% weight by volume means 30 grams of solute for every 100 milliliters of solution. Now my grams and my grams cancel. The moment I'm left with milliliters. For this question, milliliters is just fine. Remember, we chose grams and milliliters because we wanted those values to be in some way equal. So I put this into my calculator, 3.65 times 34.02 divided by 1 times 100 divided by 30. Your calculator should spit out 413.91 milliliters of solution. And let me round to 3 significant digits. So the answer is going to be 414 milliliters of hydrogen peroxide solution. Okay, so I needed 2 conversion factors here to be able to get from the units they gave me to the units that I wanted to find. And you can see that I actually ended up doing this all in one straight line, in one single equation. Of course, we could have separated these 2 steps. We could have converted moles to grams first, and then on the second line, we could have converted grams to milliliters. But this method of dimensional analysis lets us just line up all of our conversion factors in one single equation. And I really like the way that it's compact. We don't have to carry a lot of numbers over in our calculator. And so this is going to serve us pretty well. Let's try our next question. What mass of the toxin DDT is present in a seagull weighing 2 kilograms if the concentration of DDT is 99.0 parts per million? So again, make sure you pause this recording and try this on your own. And when you think you have a solution, come back and we'll do it together. So let's check it out. So we're going to put in the value that they gave us. That is not a ratio, it's just a number. And that was 2 kilograms of seagull. Interestingly, the seagull is our solution in this case. I guess that's okay. A seagull is mostly a solid. It has some gases and liquids and other solids dissolved in it, so we can use that. So this is our solution. So I need to multiply by my concentration, a conversion factor, that will let me compare the kilograms of solution to the mass of the toxin. And remember that ppm, parts per million, is a little bit different. We could have a million masses in our denominator, but instead we chose to represent parts per million as milligrams per kilogram, or milligrams per liter, whichever one was going to serve us better. So we've already taken care of the times 10 to the exponent 6 by changing these units. So that 99 parts per million, that means that there are 99 milligrams of DDT in 1 kilogram of solution. This is great. They actually gave us a unit that we needed in our conversion factor, so we don't have to convert the kilograms to something else. Kilograms and kilograms cancels out. We can just plug this into the calculator. This is going to be 2 times 99 divided by 1. Your calculator is going to spit out 198 milligrams of DDT. And this is already rounded to 3 significant digits, so we are done. Next question. How many grams of potassium nitrate, KNO3, should be used to prepare 2 liters of a 0.5 molar solution? So molar, this is another way of representing amount concentration, and what it really means is 0.500 moles per liter. And so again, this concentration is great to use as a conversion factor. That's moles per 1 liter. But our other problem is that they gave us this moles per liter, but they're asking us for grams. So I know at some point in time I'm going to have to convert between grams and moles using molar mass. So for KNO3, potassium nitrate, I've got 1 potassium that has a molar mass of 39.1, and I have 1 nitrogen with a molar mass of 14.01, and I've got 3 oxygens, each with a molar mass of 16. So first I'll plug this into my calculator, and I should get 101.11 grams per mole. All right, I have 2 conversion factors to work with. Let's see if I can put these into a dimensional analysis to get my answer. So the number that they gave me that's not a ratio, just a number, is 2 liters of solution. So I need to multiply by my concentration with liters. So I can use the concentration here of 0.5 moles per 1 liter. But they asked me for mass. I don't want my answer to be in moles. I can now multiply by my conversion factor of molar mass using 101.11 grams per 1 mole. Moles will cancel, and I'll be left with the unit grams, which is perfect. So plug this into your calculator, and you should get 101.11 grams. We can round to 3 significant digits, which will give us 101 grams of potassium nitrate. Now, when I did this problem, I looked at this answer and went, wait a minute, that's just its molar mass. How does that make sense? Well, it does make sense because we have 2 liters of solution, and each liter has half a mole. So 1 liter, half a mole. 2 liters, 1 mole. What's the mass of 1 mole? Well, it's 101.11 grams. So the math did work out here that we saw that number again. So you can see that we've used, again, 2 conversion factors to get from the units they gave us to the units that we wanted. One more question. What volume of 0.25 molar solution can be prepared using 5 grams of potassium chloride? So pause the video, see if you can get the answer, and then we'll try together. Again, I can see that I have a molar concentration, so that's going to be moles per liter, but they are giving me grams over here. So the first thing I know I'm going to have to do is find the molar mass of potassium chloride. So if I have KCl, 1K has a molar mass of 39.10, and 1 chlorine has a mass of 35.45 moles per liter, and so this sums to 74.55 grams per mole. That's one of the conversion factors I'm going to need to use in this question. So the value that they gave me was 5 grams of potassium chloride. And if I want to cancel out those gram units, I'm going to need grams in the denominator of my conversion factor. And so what I know is that 74.55 grams of potassium chloride would be 1 mole. You can see that in order to cancel out my grams and give me moles, which gets me 1 step closer to my answer, I had to use that molar mass and I had to flip the conversion factor upside down. I inverted this fraction. That's okay. This conversion factor is still true. There's still 1 mole in 74.55 grams. There's still 74.55 grams in 1 mole. I get to represent that conversion factor in either direction, and it will still be true. So I chose this direction so that my grams would cancel. Now I have moles in the numerator. I don't want moles in my answer. I want liters in my answer. They asked me what volume. And so my next conversion factor is going to have moles in the denominator and liters in the numerator. So this comes from my molarity, so 0.25 molar solution. And what that means is that there's 0.25 moles in 1 liter. Again, I had to invert this fraction so that my conversion factor would allow me to cancel out my moles and be left with just liters. Plug this into the calculator. 5 times 1 divided by 74.55 times 1 divided by 0.25. And this should give you 0.25 0.268276 liters of solution. I'll just round to 2 significant digits, and that gives me 0.27 liters of solution. Okay, so what we've worked on in this video is using concentrations as a conversion factor that let us solve for all of these different concentration calculations using one single line of this equation instead of using a few individual equations. And so if you like the unit analysis or dimensional analysis format, which I really do, then hopefully these questions are getting easier and easier for you. If you don't like this, you are welcome to keep using the formulas one at a time, the molar mass formula and then the concentration formula. But it's just a lot more rearranging. It's a lot more carrying over one answer to the next equation, and it's easy to drop digits, it's easy to make a mistake, it's easy to solve a formula incorrectly, and so I hope that you get practice with dimensional analysis and learn to love it. It's a great strategy, and when we get to Unit 4, stoichiometry, we're going to be doing a lot more of this type of question. Good luck!